Okay, so next one we want to do is problem 44 from chapter 13. A satellite is put in a circular orbit about Earth with a radius equal to 1/2 the radius of the Moon's orbit. So let's say this is where the Moon is orbiting around the Earth, and then let's say we call that Rm. And you have a satellite that has half the radius of the orbit of the Moon that's orbiting around the Earth. So this is the satellite. And you're asked to find what is the period or revolution in lunar month. In other words, you want to find what is the period, how fast does it does it orbit around the Earth, and then you're asked to express that in lunar month. Okay, so let's see how we do this, how we approach this problem. So you have two orbiting objects around the Earth. Okay, so this is like a planetary motion, and so you would use the Kepler's law, which is that relates period and the radius of the orbit. So the equation is this: 4 pi squared over gravitational constant and capital M and then R cubed. So T here is the revolution of the period, and G is just a constant. This M here is the mass of the orbit of the object that's being that is at the center of the orbit, and your R here is the radius of the orbit. So what we can do is that let's say this is the period of the satellite. So I'm going to use the S to indicate that's satellite. Ts squared, that's equal to 4 pi squared. I have my G here. I have my mass of the Earth. Okay, so I'm using the E here to indicate that's mass of the Earth. And then this is the radius of the satellite. So I'm going to use that. I'm not going to plug in any numbers just yet. And then simultaneously, we have the Moon that's also orbiting around the Earth. So you can solve equations like this. So you have the period, that is the Moon, square, that's equal to 4 pi squared, and then over G, and then you still have the same mass of the Earth, and then this is R, and then Moon, the radius of the orbit of the Moon, and then you cube it. So what we can see here is that we can just basically manipulate the equations a little bit. So we take the ratio. So you have your Ts squared, that's over Tm squared, and that's equal to all this 4 pi, all this, they just canceled because they have the same number. So you have the Rs cube and then Rm cube. So what then we are ready to plug in the numbers because your Ts, let's see what do we have here. So your Rs is 0.5 Rm. So you have 0.5 Rm, you cube it, over Rm, you cube it. So what we have here is just 0.5, you cube it. Okay. So what is the period of the satellite? When you express that in terms of the period of the Moon, that will be 0.5. You cube it, and you take the square root of that, and then Tm. Okay? So after you do the calculation, you get 0.35 the lunar year. Okay? So you can see that a lot of time you don't even have to plug in a number. You can just, based on set of equation, look at what can be, how you simplify the equations, and then this is what you get. We plug a number only at the very last stage. Okay? All right, so that's 44. Now we're going to do 45, and let me erase this first. All right, problem 45. A Martian satellite Phoebe travels in an approximate circular orbit of radius. So we have an object that's orbiting around the Mars, and so that's Phoebe, or Phobos. Phobos, I'm sorry. So that's a Martian's moon that has a radius that's 9.4 times 10 to the 6 meters. And the period is also given. So that will be 7 hours and 39 minutes. Okay, so this now, instead of the Earth, now we have Martian, we have Mars, and then this is the satellite. So I should, instead of using M, that's say Phobos, PH. Okay. So you have the moon, one of the Martian moons orbit around the Mars. So let's see. So given the radius, this is the radius, and you're given the time, and you're asked to find the mass of the Mars from this information. And you can see that that's very useful because this is how we deduce, a distant object. What is the mass of the object? Just based on the radius and also the period, which the period is easy to, that can be observed just by looking how many revolutions it made within a certain time frame. And then there are ways to deduce, what is the orbit, what is the radius of the orbit, and then you can, based on these two pieces of information, you can actually deduce the mass of the Mars. Where do we start? You have the radius, you have the period, which means that you have to use Kepler's one of the law, which is T squared, that's equal to 4 pi squared gm, and then R cubed. Now, m here again is the mass of the object at the center of the orbit. You have the t, you have the r, so it's easy to calculate the mass of the Mars. So let's do that. So you have okay, so before we do that, this is given in hours, so we need to convert it to seconds because that's the SI unit. So 7 hours, 1 hour is 60 minutes and 60 seconds, and then plus 39 times 60, and you will get, let's see, you will get 27540 seconds. Okay, so that is the period. So you plug into this equation 27540. You square it, and that's equal to your 4 pi squared, your g value, which is 6.67 times 10 to the negative 11, and then your r here is 9.4. I'm sorry. That's your m here times the mass m, and then times your r. Your r is 9.4 times 10 to the 6, and you cube it. So you can see that we have everything except the mass of the Mars. So your m, after you do the calculation, you will get 6.48 times 10 to the 23, and then that's in kilogram. Okay. So this is how this is the mass of the Mars. If you know the radius, if you know the period, then that becomes quite straightforward. Just to find the mass of the objects. Okay. And the next one we want to do is 53. All right, so 53. A 20-kilogram satellite has a circular orbit with a period. So the mass of the satellite is given, and the period is 2.4 hours, and the radius is 8 times 10 to the 6 meters around the planet of unknown mass. If the magnitude of the gravitational acceleration on the surface of the planet is, so let's say the AG here is 8 meter per second square, then what is the radius of the planet? So in other words, this is a diagram. You have an unknown mass of the planet, and this is a satellite that's orbiting around that. So this is the radius of the orbit is given, and the period, the revolution is also given. You're also given additional information. That is, when the object plays the acceleration on the surface of the planet is 8 meter per second square. So you're asked to find the mass. You're asked to find the radius, not the mass. You're asked to find the radius of the objects. In other words, what is that capital R? Okay, so we can see that with period, with the radius of the orbit, we can easily calculate the mass of the object. Although the mass of the object is not known, but we can actually calculate. So once we calculate the mass of the object, let's use capital M. So once we calculate the mass of the object, then based on gravitational acceleration, gravitational force, we know that F equals gmm over the separation. And that's say if you have the separations, right? So if you have an object that is located at the surface of the object, then that gives you the distance off. So let's do that. So that's first of all apply Kepler's law. So you have t squared, that's 4 pi squared over gm, and then rq. So we have, again, the 2.4 hour needs to be converted to minutes, seconds. So hour, 60, 60. So you should have, let's say, what do we have? So you have 8640 seconds. So once you have that, then we can plug into this equation. So you have 8640, you square it, and that's equal to 4 pi squared, and then you have your 6.67 times 10 to the negative 11, and then times the mass of the planet, and then times the radius. The radius is this, so you cube it. So you can calculate the mass of the planet is equal to 4.06, and then times 10 to the 24th kilogram. So this is the mass of the object. Once you have that mass of the object, remember your gravitational acceleration is defined as gm over r, okay, over r squared. So this is your definition of the acceleration of gravitational acceleration of the object. So what we have here is that you have your m already calculated. So and then your a is given. So you have your 8. That's equal to 6.67 times 10 to the negative 11, and then times the mass, which is 4.06 times 10 to the 24th, and then over your r squared. So what is the radius? The radius of the object, after you do the calculation, that is 5.8 times 10 to the 6 meters. Okay? So you can see that this is actually a two-step process. It's not one step. You will first of all you need to figure out what is the mass of the object, and then use the information to because your A is basically equal to gm over r squared, and then to calculate the radius of the object. Okay? So that's that.